Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders 2001, problem number 4. It has two parts. First part, we wish to prove that natural log of 1 plus x is less than x for positive numbers x, and moreover, part B, let a be some number greater than 0. We wish to prove that the limit as n goes to infinity of n times the integral from 0 to 1 x to the power of n over a plus x to the power of n dx equals natural log of a plus 1 over a. So here are my hints for this problem. First part is really easy. Just consider function f of x equals x minus natural log of 1 plus x and differentiate it to show that it's probably increasing. To prove b, probably you are supposed to use part A to prove b, but I will do without it. Prove b by substituting x to the power of n equals t and use the powerful theorem, namely the monotone convergence theorem, to compute this limit. So give this problem a try and I will see you in just a minute. Right, so let's tackle part A first. So let f of x be equal, as I suggested, natural log of 1 plus x minus x for x greater than or equal 0. Notice that then we have the following. The derivative of our function is 1 over 1 plus x minus 1, which is x over x plus 1. And obviously, since x is greater than or equal 0, this is actually greater than 0 for x greater than 0, which means that our function is strictly increasing. F is strictly increasing. It's strictly increasing on the interval 0 plus infinity. And what is f of 0? Well, f of 0 is natural log of 1 minus 0, so it's 0. Which means that our function starts at 0 and then it increases. Which of course means that for every positive number x, f of x is greater than 0. Which closes the proof of part A. Part B. Let's take our integral first. Integral from 0 to 1 of n x to the power of n a plus x to the power of n dx. I will make a substitution. Namely, I will substitute t equals x to the power of n. Why? Because now, well, notice first that means, since we are integrating over positive numbers, this means that x equals nth root of t. Moreover, dt equals n times x to the power of n minus 1 dx, which means that x dt equals n x to the power of n dx, but x is nothing else but nth root of t dt. Right? And what about the boundaries of integration? Well, notice that since x is from 0 to 1, then obviously t is also from 0 to 1, because 0 to the power of n is 0, 1 to the power of n is 1. So our integral can be rewritten in the following manner. It's just the same as the integral from 0 to 1. Instead of n x to the power of n dx, we can put nth, maybe I will write entire thing in yellow, we can put nth root of t dt, and in the denominator we have a plus t, just that. And this is arguably simpler because n appears only in one place. And now it's time to use the monotone convergence theorem, because note that we have the following. As n increases, the values of our function increase, yes. Well, why is that? Well, we just need to compare the numerators. Notice that this inequality is equivalent to saying that t to the power n plus 1 is less than t to the power of n, or we can put weak inequality, doesn't really matter, less than or equal, and notice that this is equivalent to saying that t is less than or equal 1, which it is. So, by the monotone convergence theorem, we can put our limit inside. So, limit as n goes to infinity of the integral from 0 to 1 nth root of t dt a plus t, we can take this limit inside. Well, and what's the limit? Pretty easy to see that, maybe I will write it here, that nth root of t converges to 1 if t is a positive number, and of course nth root of t converges to 0 if t equals 0. But notice that convergence to 0 happens only at one point, so we can ignore this point, and we can just write that it is integral of dt a plus t. Very well, but now we have elementary integral. The antiderivative of this function is natural log of a plus t. We have to evaluate it from 0 to 1. So it's natural log of a plus 1 minus the natural log of a, which of course can be rewritten as natural log of a plus 1 over a, which was exactly our goal. It was exactly what we wanted to prove. And that closes our proof. It's a very nice problem, which was trivialized by the monotone convergence theorem. Without it, this problem would be harder. So yes, that's it. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.